Okay, so I've broken up Chapter 8 into a couple chunks. So all we're going to go over today is Section 8.1 that actually tells you how to subnet. And a teeny tiny bit about VLSM. If you go to the class resources page on Moodle, I have posted, Johnny reminded me that I love the networking doctors. They have a bunch of YouTube videos. It's a guy who has a doctorate in networking, and the way he explains subnetting and VLSM is like really broken down, really easy to understand. So down here I've made another category called subnetting where I put links to those, especially once you get out of this room and me talking, going back and looking over those again will probably help you a lot if you're confused. They are very, very good videos. Okay, Chapter 8, here we go. We are just going to go through 8.1 and talk about subnetting today. So, we're going to talk about why we subnet, how we subnet. We're going to talk about the math behind it. You were already kind of introduced to this in your lab work last week, whether you knew it or not. So I tricked you. You're welcome. So, a broadcast domain. We know what a broadcast is, right? That's when we're advertising out to everybody on the LAN segment.
Whole bunch of F's, is that what you mean?
Yes, yes. When we see all 255s or we see all F's in our address, depending whether it's IPv4 or 6, that's how we know we have a broadcast address. So each router interface is going to create its own broadcast domain. So that means that the thing that separates broadcast domains is a router. So if a broadcast occurs anywhere on this LAN segment, it's going to go to the router's going to see that it's a broadcast, and then it's going to drop the packet. So a router is the device that breaks up broadcast domains. That's the first thing to know today. Now the problem when we start adding more and more computers, more and more users, more and more switches, and different things on the network, we're going to have a lot of broadcast traffic occur. So this will eventually slow things down. These broadcasts are bouncing all around. People are trying to figure out who belongs to what address, and we have a large broadcast domain. More and more broadcasts are going to lead to more and more network issues. So the solution to this is to not have a large broadcast domain, right? It's to reduce the size of the network and create multiple broadcast domains. So instead of one big network of 400 users, now I've got two networks of 200 users. Subnetting is what allows us to do that. We call these smaller networks, these chunks of networks, subnets. So, depending on the way the network is set up and the way the building is laid out can determine how you're going to set up your subnets. For example, this is a 5-story building, and they've decided that every story should have its own, or every floor should have its own subnet. So that's how they're going to organize the computers there. So it's reducing the overall network traffic. It improves your network performance. It enables the administrator to implement security policies for one subnet versus a different subnet. So for example here, we can put our cybersecurity lab on its own separate subnet so it can't communicate with anyone else, because we do different things in there, right? I know like in security classes sometimes we create viruses, we attack each other, we do different things in there. So you don't necessarily want that traffic mixed up with all the other traffic on the network, because that could cause some problems. It may need more security than the other labs here do. So you can also group things by organizational unit. Again, as an administrator, it's your choice which one you'd like to pick, which one makes the most sense. So this one we've divided into administration, human resources, students, and accounting. So this is kind of by role. They've subnetted by role. Or they can do it by device type. That's what we do here. All the wired computers are separate from all the wireless computers, are separate from all the security cameras because they require different roles. So in this case, they put all the hosts on one subnet, all the servers on another subnet, and all the printers on their own subnet. We talked a little bit last week about the octet boundaries. That's when we had the N's and the H's, for the networks and the host. So every interface on a router is connected to a network. The IP address and the subnet mask configured on the router interface are used to identify that specific broadcast domain. That's how we refer to it. So the prefix length and the subnet mask are different ways of identifying the network portion. So I can say /8. /8 says 8 network bits, right? 8 bits turned on from left to right, right? So here's an example of that. Our mask is 255.0.0.0, and our subnet mask, if we convert it to binary, is just 8 ones. So those are two ways of referring to the exact same thing. Yes, sir?
I remember, it was either one of the quizzes or the exams, there was questions on how can you tell it was Class B, and had like the /8 octet and everything on there. I couldn't figure out how to go through and do the mathematics to it. Well, was that pretty much subnetting on that question?
Yes. There's some subnetting mixed in Chapter 7 that's a little, really not quite ready for it. So remember, you can take that Chapter 7 quiz over and over. That's fine. I'm hoping maybe this chapter will clarify some things a little bit. So the more host bits that we borrow, the more of these that we borrow, the more subnets we're defining. And you'll definitely see some examples of that as we go along. So if we're subnetting at the octet boundary, meaning it's either at the end of the first octet, the end of the second, the end of the third, we come up with something like this. So if we're subnetting with a /16, we have our different subnet addresses, and this is what's changing. The second octet is what's changing. Why? Because it's a /16. You'll see here in a /24, the second and the third can change. So this is just a look at what we're going to be working out here. We've got the subnet address, and we've got the range of usable hosts and the broadcast. The subnet address is the same as the network address. It's the first one. It's the one we can't use. We know the broadcast address is the one we can't use either, right? Because it's used just for broadcasting. So let's assume that an enterprise has chosen the private address of 10.0.0.0/8 as its internal network address. So that means that the network address can connect over 16 million hosts to one broadcast domain, right? Now that's obviously too many. There's lots of potential for issues there. So what would make more sense is to take that and to break it down into smaller chunks. Break it down into a /16 or /24, depending on how many hosts they need. If they had, for example, a /24, that's going to break it down even further into over 65,000 subnets, which is a lot of subnets, right? But they're going to have a smaller number of hosts in each one. So that'll be 254 usable hosts and 65,000 subnets. So 65,000 departments, essentially, or organizational units, or however you want to break that up. The /24 is one of the ones, like in practicality, that we see the most. Okay. Now, what we've been talking about, the /8, the /16, the /24, that's on the octet boundary, right? That's at the end of the octet. Now that's the easiest way to do it, but that doesn't always give us the right amount of hosts. So that's called classful subnetting. This is classless subnetting, right? We're not sticking to that class A, B, C. We're changing bits a little bit. So this in a Class C, classless subnetting, and you can see that because it's more than 24 bits turned on, right? So in a /25, you can borrow 1 bit from the 4th octet, which is this right here, and that creates 2 subnets with 126 hosts each. We'll talk about the math, how we get there in just a second. This is what, when they refer to borrowing bits, this is what it looks like. So normally, in a Class C address, our line would be drawn right there on the octet boundary, right? But in this case, we're taking something that's normally designated for the host, and we're turning it into a network bit. Then we're going to use those formulas that were in that lab that we did last week, the 2 to the h minus 2 and all that, to calculate what these are. So with a /26, you're borrowing 2 bits. Remember, 24 bits turned on, 1, 2 is 26. That gives you 4 subnets with 64 hosts each. If you're a math person, you can already start to see a pattern developing here, right? You can see doubling occurring on the subnets for every 1 bit you move over, and then halving almost. We have some of the -2 that messes that up, but when you're classless subnetting Class C, this is what it looks like, all the way to a /30. So borrowing 6 bits from the host side gives you 6 more network bits, which gives you 64 subnets with 2 hosts each. Now think about that for a second. 2 hosts each. When would you use just 2 hosts per subnet? This is one of the exam questions this week, so I want to hit it. If you've ever heard of point-to-point communication,
Yes.
one building to another building, right? You only need 2 hosts. So /30 is completely normal, right? We see /30 is used a lot. Now, like a /31, you have 0 hosts. A /32, you have 0 hosts. But a /30 is as high up as that goes. What's important, I'm going to show y'all a couple of videos that show you just exactly how they get these numbers, and it will help it make a lot of sense. But what I want you to understand is that with a /25, the math is always the same. Anytime you have a /25, you have 2 subnets and 126 hosts. Every time you have a /28, you have 16 subnets and 14 hosts on each subnet. It's the same thing every time. Okay, now I'm going to show you all a couple videos of how they arrived at these that I think are helpful.
Now, I want to take a moment to point out that subnetting makes sense from the binary perspective. In other words, when we take the IP address and the subnet mask and convert them to binary, I have the IP address on this row here, I have the subnet mask on this row, converted to binary, that the computer and the router are able to logically AND or combine the IP address and the subnet mask and find the network address. In other words, this ANDing process is a logical process of ANDing. So a true and a true makes a true, 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 false and a true makes a false. And if we do that and logically AND the IP address with the subnet mask, we get the network address. So 192.168.1.10 logically ANDed with 255.255.255.0 produces the 192.168.1.0 network. This is at the core of the IPv4 address and subnet mask, and subnetting in general. What about non-classable subnet masks? We've seen that the Class C subnet mask is /24. We've seen the Class B subnet mask /16 and the Class A subnet mask /8. But what if we use classless masks? In other words, what if we have a /25 subnet mask or a /18 subnet mask, creating a 255.255.192.0 subnet mask? Or for that matter, a /12 subnet mask, 255.240.0.0. How does that work, and how does that change the networks that are created by the combination of the IP address and the subnet mask? This is called subnetting. I'll explain it using an example scenario. let's start with a classic Class C network, like 192.168.1.0 with a /24 or 255.255.255.0 subnet mask. If we want to subnet this 192.168.1.0 network, what we need to do is go into the subnet mask in binary, which we can see on this row right here. And what we do is, to change the subnet mask, we borrow bits from the host portion of the address. This is done from left to right. So I could take this first 0 here on the left and change it to a 1. And now I've effectively changed the subnet mask from /24 to /25. In other words, if I convert this back to decimal, it's now 255.255.255.128. This completely changes the nature of the network. We now have a /25 subnet mask, and we only have 7 host bits. So, starting from a /24, we now have borrowed 1 bit from the host portion. We call this 1 bit a subnet bit. If we look at it from the perspective that we started with /24, we've added 1 bit. So we could say that subnet bits, we now have 1 bit, or 2 to the first power, creating 2 subnetworks. Host bits, we have 7 zeros now. So host bits are 2 to the 7th power, or 128, minus 2 for the network address and the broadcast address, leaving us with a total number of possible hosts on the subnets of 126. So by borrowing 1 bit from the host portion of the address, we create 2 subnetworks, each subnetwork with 126 hosts. The subnetworks are the 192.168.1.0/25 subnetwork and the 192.168.1.128 subnetwork /25. We can prove that this is the case using logical ANDing to prove how the router or a computer would take an IP address with this particular /25 subnet mask and derive the resulting network address. In other words, let's put in a host address. I'll put in the host address here, and I'll say, let's put in the address 68. So I changed this to a 68. So now we've got host 192.168.1.68. So this needs to be a 1. That's the 64. And then we need to add the 4-bit here. So now we have 68. If we logically AND the IP address here with our new subnet mask /25 here, let's see the result. We'll get a 1, a 1, a 0, 0, 0, 0, 0, so that's 192, and then here the result is 1, 0, 1, 0, 1, 168, and then all zeros here, and a 1. This is a 1. And now, if we look at this last octet, a false and a true makes a false, a true and a false makes a false, and then we get all zeros here. So the address, the network address, is the 192.168.1.0 network. So host number 68 is on the 0 network. Well, this makes sense because if the next subnet is 128, if we put in a host address larger than 128, we'll see if it falls in this subnetwork. So let's change it slightly. I'll change the host address to 138. So now I'll change this, put that as 0. So there's a 128 bit. I'll make this a 1. And I'll put a 1 here. So 128 plus 8 plus 2 is 138. If we do the ANDing again, we see that a true and a true makes a true, and then we have falses all the way, and now the resulting network address is 128. So when we take the IP address with the /25 subnet mask, we see that the network address is 192.168.1.128. So we've created two subnetworks from the single 192.168.1.0/24 network. We've created two subnetworks. The subnetworks go from 1.0 all the way up to 1.127, with 0 being the network address and 127 being the broadcast address. And the second subnetwork starts at 128, so this is the network address because it's the first address, all the way up to 255, and since this is the last address, this is the broadcast address. In other words, the first address in the subnet is the network address, and the last address in the subnetwork is the broadcast address. This process is called subnetting.
Okay, so that's what the logical ending look like. That's how they get that information. But as you go along, you'll see, if you can establish what the subnets are, then you can look and say, oh, well, 168 fits between 128 and 255, so it belongs in that subnet. But that is how they're actually getting that information. Now, this video teaches you how to make those subnets. How do you determine what each subnet is? When it says it breaks it into 4 subnets with 62 available hosts on each one, how do they establish what those subnets are? So this, to me, is the easiest way to subnet, and this is the way Cisco teaches it, with what they call the magic number. Sometimes you hear it referred to as the increment value, but it's essentially the same principle. So this is the good stuff. This is the video that's the good stuff.
This video focuses on subnetting and how to find your subnetworks easily and quickly using the magic number trick. Let's say we're subnetting a 192.168.1.0 network /24. I have the IP address and subnet mask in decimal here, and I have them listed in binary here. The network portion of the subnet mask and the host portion of the subnet mask. To subnet this network, what I can do is I can borrow 1 bit from the host portion of the subnet mask, and now I have 1 subnet bit. This changes the subnet mask from /24 to /25. If I borrow 1 bit from the host portion, I have 1 bit, or 2 to the first power, makes 2 possible subnetworks. The subnetworks I've created are the 192.168.1.0 subnet and the 192.168.1.128 subnet, both /25. The hosts on each network are 126 usable hosts. We have 7 zeros here, and 2 to the 7th power is 128, minus 2 makes 126 usable hosts per subnet. If I decide to borrow 2 subnetwork bits from the host portion of the original 192.168.1.0/24 network, I now have /26. I've borrowed 2 bits, so now I have 2 to the 2nd power of subnet bits, so I have effectively 4 subnetworks. The 4 subnetworks are listed here. For host bits, I have 6 zeros in the host portion of the address, and 2 to the 6th power is 64. Minus 2 for each subnet makes 62 usable hosts per subnet. The subnetworks that are created are the 192.168.1.0 subnet, the 64 subnet, the 128 subnet, and the 192 subnet. Notice how the number of borrowed bits and the number of host bits determines a lot about the subnet. If I borrow 3 subnetwork bits, I now have a /27, so it goes from /24 to /27. I have 3 subnet bits. 2 to the 3rd power is 8. 2 times 2 times 2 is 8. And you can see that I now have 8 subnets, or 8 subnetworks, created from the original 192.168.1.0 network. Each subnet is now /27. Notice that there are now 32 hosts, or 30 usable hosts, per subnetwork. We could go up to /28, And now I have 4 subnetwork bits. Notice that the subnet mask has changed from 255.255.255.0 when it was /24 to now 240. I now have 16 subnetworks, or 2 to the 4th power, and there's 2 to the 4th power of hosts per network. So there's 16 or 14 usable host addresses per subnet. Borrowing 5 bits looks like this, and borrowing 6 bits looks like this. I've now borrowed 6 bits from the original 8-bit host portion of the original /24 network, and I now have 2 to the 6th power of possible subnetworks, meaning I have 64 subnets. The host portion of the address is now only 2 bits, or 2 to the 2nd power, meaning there's only 4 host addresses per subnet. Now if you have 4 host addresses, you have to leave room for the network address and the broadcast address, so 4 minus 2 leaves only 2 usable hosts per subnet. You cannot go higher than a /30 subnet mask. Otherwise, you'll not have enough room for usable host addresses. In other words, we can't borrow any more bits from the host portion, or we won't have enough addresses for hosts. You might be asking yourself how I was able to discern the different subnetworks from the subnet mask or subnet bits that were borrowed. There are many different ways to derive the subnetworks from the subnet mask, but my favorite is the magic number technique. The magic number is simply the place value of the last one in the subnet mask. So in this situation, we have a /25 subnet mask. We have 25 ones, and the last one is the one here all the way on the right, highlighted in red. This one, if we look at it according to this octet, is in the 128th place. If we think about the place values of 8 bits, this is the 128th place. So the magic number in this situation is 128. The magic number tells us where to find the networks. It tells us that the networks will go up by 128. So in this case, the first network, which is always 0, so 192.168.1.0/25, and from there the networks go up by 128, so the next network is 192.168.1.128. Let's see how this works, borrowing 2 bits from the host portion. Now I have borrowed 2 bits from the host portion of the subnet mask. The magic number is now the last binary one, which in this case is in the 64's place. So the magic number is 64. The magic number tells us how to find our networks and lets us know that the networks will be going up in increments of 64. So for instance, the first subnet is always 0, so 192.168.1.0/26. The next subnet is 64. 64 plus 64 is 128, and 128 plus 64 is 192. You can see how the subnets are going up by 64. There's only 4 subnets because we've borrowed 2 subnet bits. Also, we can go no higher than 192 because 64 plus 192 is 256, and that's too large a number. Let's see how it works with 3 bits. With 3 bits, we now have a /25, 26, 27 subnet mask, /27 subnet mask, in decimal 255.255.255.224. The last one in the subnet mask is our magic number. In this case, it's in the 32's place in the binary conversion table. So the magic number is 32. If we look at the networks, we'll see that they go up by 32. The first network being 0, 192.168.1.0/27, then the 32 subnet /27, 64, 96, 128, 160, 192, and 224. The subnets go up in increments of 32.
Let's stop that for a second. Does everybody understand that concept? Finding the binary value of the last one and then incrementing subnets by that value.
All the
Yes.
way up to how many it adds up to in the binary.
Right. If you get to 255 or past really 255, you have to stop because that's not a valid IP address. Right. So make sure everybody understands that because that is a big deal.
Following the magic number. Now that we see the pattern and how the last borrowed bit affects the location of the subnetworks, let's try it with a /28 subnet mask. Now I have the 192.168.1.0/24 network. I want to subnet it, changing it to /28. /28 means I borrow 4 bits in the subnet mask, so I now have 28 ones counted from left to right. 255, 255, 255, 240 subnet mask. 128 plus 64 plus 32 plus 16 is 240. The last one is in the 16's place. This is the 128's place, the 64's place, the 32's place, the 16's place. So the magic number is 16. We'll see that the networks go up by 16. The first network is always 0, so 192.168.1.0/28. I'll copy this and paste it, and the next network will be the 16 network. Why? Because the magic number is 16, because the last one is in the place value of 16. The next network will be 32. And the following network will be 48. And after 48, 64. And so on and so forth. The networks will go up by 16. In each network, we have the host bits, 4 bits for hosts, which is also 2 to the 4th power of 16. So the network will go from 0 up to 15, with 0 being the sub-network address or network address, and 15 being the broadcast address, and the next subnet is the 16 subnetwork. Now let's try creating /29 subnets. We can see that that involves borrowing 5 bits from the host portion of the subnet mask, and that the last one is in the 8th place. So the magic number is 8. The networks will go up in increments of 8. So starting from 0, we'll have the 8 network, and the 16 network, and the 24 network, and so on and so forth, all subnets being /29. For the /30, we see that the last one is in the 4's place, and that the networks will go up by 4. So similarly, the networks will go up in increments of 4. So the first network is the 0 network, then the 4 subnetwork, then the 8 subnetwork. Each subnetwork will have 4 host addresses, in this case 0 to 3. 0 will be the network address, 3 the broadcast address, and the addresses between 1 and 2 will be the usable host addresses. Only 2 usable host addresses in a /30 subnetted network. You might ask yourself, will this technique, the magic number technique of looking at the place value of the last one in the subnet mask, work in other subnetted octets? In other words, if we're starting from a class B /16 network address, or a /8 class A network address, would this technique work? And it does. For instance, if we take a 172.16.0.0 network /16, you can see in this scenario, I've subnetted it to a /23 subnet mask. In other words, I've taken the original 16 network bits and borrowed 1, 2, 3, 4, 5, 6, 7 ones from the host portion of the subnet mask. In this situation, the last borrowed 1 is in the 2's place. So the magic number in this situation is 2. This means that the subnets will go up by 2 in this octet here. So in other words, our first subnet will be 172.16.0.0/23, and the next network will be 172.16.2.0/23. The only difference is now, instead of 16 host bits like we would have had in a /16 network, we now have 9 host bits. So 2 to the 9th power, meaning we have 512 minus 2 would be 510 host addresses that we can assign. In other words, the network goes from 0.0 all the way up to 172.16.1.255. So the first usable host address would be 0.1, and the last usable host address would be 1.254. The next subnet starts at 2.0. After that, the networks continue to go up by 2. In other words, the next subnet will be the 4 subnet, and then the 6 subnet, and the 8 subnet. Notice that the networks are going up by 2, but in the 3rd octet, not in the 4th octet. The only difference not to be confused on is the larger number of host addresses that you'll experience when you subnet in this octet or in the 2nd octet. You can see how the magic number technique can help you quickly locate the networks or subnets.
Okay, so that is essentially the magic of subnetting. So, we're going to do lots of example problems on this. I don't mind sticking around in subnetting for a while to make sure everybody gets it, because that is important. So this is an example of classless subnetting. Again, we're going with a class C. Generally, we kind of start learning with C and then we move back to B and A. So this is a /25 network. Here's the original address and the original or the default subnet mask for a class C. Then we're going to borrow that bit that makes it a /25. It's going to give us the new subnet mask. So we're borrowing that 1 bit. That's what gives us the /25. So it's going to change. We're going to have 2 subnets. The first one is the .0 subnet. That's the first. And then the second one is the .128 subnet, just as they showed in the video. Practically, how this happens on a network, we'll take these 2 subnets, we'll apply them to the network. So in this case, we've got a router with 2 switches. These switches are different LAN segments. This switch is going to be assigned the .1.0 network. This one will be assigned the 1.128 network. So this is how we're actually physically separating these things and then assigning addresses to them. The /25 is telling this network, these are the ones that belong on your side of the network. These are the ones that belong on the other side of the network, essentially. So our address range for the 1.0 subnet, we know that our addresses are going to go from 1.0 to 1.127. Okay? Then to get our first host address, we're going to just add the next address. So it's a 1.1. And to get our last usable address, we're going to take this address minus 1. So that gives us 1.126 on the other side as well. So you can see that the broadcast address here is 1.255. 255 is the highest binary number we have. So we can subtract from that to get our last host or add to the first address to get our first host address. So we know we have our range of .1 to .126. That's all addresses that we can assign in that subnet. Right? When this gets assigned to interfaces, this is what it looks like. So we have to Gigabit Ethernet 00, which is right here. We're assigning it the first available host address. Okay. And then for 01, we're assigning it the first available host address in the second subnet. So first subnet, second subnet. That's how that actually pans out when you practically do it in Packet Tracer. So you'll notice that PC1 got one of the available host addresses. PC2 got one of the available ones in that range. But that's how that actually gets put into Packet Tracer. For PC2, since we have a static address we want to assign to PC2, we're going to have to go in the TCP/IP properties and tell it that information. So that's going to give us the IP address of 192.168.1.130, the subnet mask of 255.255.255.128, because we have that one bit turned on that makes the two subnets. And then our default gateway is going to be our interface that goes to the router, which is this. Okay? So this PC's default gateway is its way out of the network through Gigabit 01. So some of these subnetting formulas that we've talked about, hopefully they'll kind of start to make sense. When you're talking about network bits, 2 to the n gives you the number of bits borrowed. And you'll notice if we borrow 1 bit, 2 to the first power is 2, that gives us 2 subnets, right? If we borrow 2 bits, 2 to the second is 4, that gives us 4 subnets. Those are the formulas that you did in the very first lab we did last week. 2 to the n minus 2. I prefer 2 to the h minus 2 because h stands for host, but whatever. Same thing. If I have 1 network bit I borrowed, I've got 7 host bits just sitting there. So 2 to the 7th minus 2 gives me my 126 valid hosts per subnet. So just using that math, you can determine pretty quickly where your host and where your networks are and how many addresses you're going to have available for each thing, right? Okay, so we've talked about creating 2 subnets. Now if we're creating 4 subnets, we have a /26. This is what it looks like. So I have 64 is my increment value, right? Because that's the second bit in that octet is on. So you're going to see changes occur by 64s now. Okay? So in practicality, that's how that's done. So here now we're borrowing 2 bits. That gives us, they go through this kind of binary stuff here to get this. If you can add by 64, you'll get the exact same numbers. But 0, 64, 128, 192. Now I have 4 subnets, and that's the network address of those 4 subnets. If I know that, I can figure out the broadcast address and the usable addresses, right? For the first subnet, if I have a 1.0, and for the second I have 1.64, what's my broadcast address for the first subnet? 1 less than that one. .63. My usable addresses are .1 to .62. That same pattern continues every single time. If you can figure out how to break up the subnets, you got it made in the shading. Okay? So here, in our first subnet, here's the example of that. We start with 1.0. We always start with the 0 subnet. We know we're incrementing by 64. That's how we get 1 less than 64 is our broadcast address. The address that comes before that is our .62, our last usable host address. And then 1 more than that is our first usable host address. We're not wasting any IPs, right? Because we're saying the next one is the next one we're going to start using, and the one before that one's the one we're going to start using. So anything in the 1 to the 62 range is a usable IP address I can use on that subnet. These are the address ranges for a couple of the other subnets. Again, using the same .0, .64, .128, .192, but how they're arriving at those addresses in the middle of that. So same as before, if we're going to establish these, put these on links, this is what it looks like. Gigabit Ethernet 00, which is here, which is our way out, is going to get the 1.1. It's going to get the first usable address on the first subnet. Gigabit 01 is going to get the first usable address on the second subnet. And serial 000 is going to get the first usable address on the third subnet. So in this case, all those subnets didn't necessarily get used, right? The fourth subnet didn't get used. It's better to have too many than to have not enough, because then you can't plan properly. So here's a little video to show how they got those 8 equal size subnets. We just saw how they got 4, now we're going to go through 8.
In this situation, we need to create 8 equal size subnets starting from the 192.168.1.0/24 network. We actually only need to create 5 subnets, but since subnets are created in powers of 2 starting from 2, we'll need to create 8 equal size subnets in order to accommodate the 5 subnets necessary in this diagram. So first I write out the subnet mask in binary, 24 ones for a /24 network. We're going to borrow bits from the host portion of the subnet mask. If we borrow 3 bits, we've borrowed 2 to the 3rd power of bits, and 2 times 2 times 2 is 8, so this will create 8 subnets. The last one in our new /27 subnet mask is in the 32's place if we look at it according to an 8-bit binary conversion table. So the last bit is in the 32's place. This lets us know that the subnets will go up in increments of 32. So the first network will be the 0 subnet /27, and the next subnet will be the 32 subnet /27, and then going up in increments of 32, 32 plus 32 is 64, and then the 96 subnet. After 96, we'll have the 192.168.1.128/27 subnet, and then the 160 subnet, the 192 subnet, and the 224 subnet. So as you can see, we have 8 subnetworks going up in increments of 32, the 0, 32, 64, 96, 128, 160, 192, and 224. We can use any of these 8 subnets to accommodate the 5 subnets that we'll need to address all of these networks.
We'll have to talk about that in section budget. Okay, so in that video they created 8 equal sized subnets. Okay, so in a situation that requires a larger number of subnets, you're going to have to borrow more host bits. So we move up in class. So for example, the network address 172.16.0.0 has a default subnet mask of 255.255.0.0. So you've got 2 more octets to play with, playing with the zeros. So you've got 16 bits, or 2 to the 16 worth of addresses that you can have in there. So for every possible scenario for a /16 prefix, you can start to see you have 2 subnets, again, because you only have that 1 bit to work with for the network bit. And then you've got a possible over 32,000 hosts because you have all these host bits to work with. And so you can kind of see as you work down, if you start from a /16, you're just doing the same math problem over and over, right? You're just looking at powers of 2. So with a /22, you've turned on 6 bits in the 3rd octet, and that gives you 64 host nets with 1,022 addresses on each one. If you needed to create 100 subnets, most of the problems you'll be given, they won't give you something that can exactly be achieved. You'll have to give them a little more subnets. So if I'm in a /16 and I want to create 100 subnets, I have to borrow 7 bits and actually give them 128 subnets, right? If I borrow 6, I only give them 64. That doesn't meet what they want. They want 100 subnets. So in that way, we kind of waste addresses. So we'll talk about how we fix that exactly. So that would give us a /23. So we went from a /16 to a /23. And you can see that where our last binary value is as a 2. So we have tiny little networks, right, with they increment by 2. One of the most important things I can teach you about subnetting is wherever the octet where the last 1 is, that's the octet that changes when you actually start subnetting and making those addresses. We will go over this more when we come back on Thursday. So if you don't understand everything today, that's okay. So again, calculating those hosts for a /23, this is showing how we're getting the first subnet is always the 0 subnet, it's always zeros. And then we're incrementing by 2, which makes our broadcast address 1.255. Like rolling over the odometer in your car, right? When you get all 9s, it has to go to 1 on the next place and roll over to 0. The same thing is kind of happening with those IP addresses. This is when you're supposed to be impressed that I know what an odometer is. Or HALAC. Okay. If I want 1,000 subnets, I have to keep moving back. The more I want, the more I have to keep moving back. So in this case, I've got to start with a 10 dot network. Okay? So it's got a default subnet mask of what? It's class A, right? Falls in the class A range. So what's the default subnet mask? How many 255s are there? 1. 255.0.0.0, right? So I'm starting with a /8 network. That means there's 8 bits for the network and 24 bits for hosts. So I have a lot more options as far as hosts go in there. So 2 to the 10th is 1,024 subnets, so I'm borrowing 10 bits. Okay? And that's what that looks like. So normally, I only have 8 bits. I'm borrowing 10 more, and that's going to give me what I need. So that allows me to create 1,024 subnets if I have a /8 network to start out with. And you can see my increment value is 64 because it ends in that 2nd place. So I'm going to have the incrementing is going to start in the 3rd octet because 1, 2, 3, that's where the changeover occurred. So that's going to give me the subnets that I'm looking for.
in classless subnetting, we've seen how we can borrow bits from the host portion of the subnet mask, and that the last one that's borrowed is the magic number, meaning that the last one, if we look at the place value of the 8-bit grouping, the last one, in this case, is in the 32's place, so the networks go up by 32. Starting with the 0 network, we have the 32 network, then the 64, 96, 128, so on and so forth, but the networks go up by 32. What about when we're subnetting from a Class A or Class B network address and subnetting generally in the other octets? Let's take a look at another example. This time we have a 10.0.0.0 network address and a classful Class A subnet mask, and we're going to subnet it. So we've taken the 8 bits and borrowed 3 bits, and now we have a /11 subnet mask. The last one in the subnet mask is still in the 32's place. If we look at this 8-bit grouping in this octet right here, the last one is still in the 32's place. So the networks will go up by 32. So the networks are the 10.0, 32, 64, 96, and they're going up by 32, but in the second octet. The only difference is now we have a lot more host addresses. We have 8, 16, 21 zeros for hosts, which means there's over 2 million hosts per subnet. For instance, if we take a look at this 10.192.0.0 subnet, the next subnet is 10.224. So that means that the host addresses go from 0.1 all the way up to 10.223.255.254 as the last usable host, and 255 is the broadcast. The next address is 10.224.0.0, which is the next subnet. All of these subnets are now /11. What about a more difficult scenario? In this scenario, we need to create over 300 equal-sized subnets of 20,000 hosts each, starting from the 10.0.0/8 network. So we need to create a lot more subnets, and we need a lot of hosts. Looking at this situation, we know that we're going to need to borrow bits from the host portion of our subnet mask. The question is, how many bits will we borrow? If we borrow 1 bit, we have 2 subnets. Now we have 4 subnets, 8 subnets, 16, 32, 64, 128, 256, 512. If we borrow 9 bits, we'll have 512 subnets that we create, and that will be sufficient to meet the demand for 300 equal-sized subnets. What about the requirement of 20,000 hosts each? We have 15 zeros left for hosts per subnet. 2 to the 15th power is 32,768. Minus 2 would be 32,766 hosts per subnet. That meets the requirement of having at least 20,000 hosts in each subnet. So this scenario would work. You can see here that I've now highlighted the borrowed bits from the subnet mask. I've also converted it to decimal here, 255.255.128.0. And I've already ascertained that the last one in the subnet mask is in the 128's place, so the magic number is 128. The subnets will still go up by 128, but they'll also need to go up for every number possible in the second octet. If we look below here, we can see our subnets. The first subnet will be the 10.0.0.0/17 subnet, then the 0.128 subnet, then the 1.0 subnet, then the 1.128 subnet, and as you can see, we're iterating through every possible number in the second octet, and then going up by 128 in the third octet. If I was to list out every possible subnet, we'd go all the way up to 10.255.0.0, and the next subnet would be 10.255.128.0. /17 is our last subnet, for a total of 512 subnets. In a situation like this, there's many more subnets and many more hosts per subnet, but the rule of the magic number still applies.
Okay. So when you're planning all this, I promise we're towards the end. When you're planning all this, you need to know how many hosts are going to be on the network. When you get into the higher Cisco classes, you'll actually have to plan like for 10% growth and things. You have to know how many hosts you need, and you have to know how many subnets you need. You use that information to plan out what your subnet mask is going to be and to make sure that you have enough subnets with enough hosts on them to satisfy the needs of the network. So if you're subnetting based on organizational structure, like we talked about in the beginning, you're separating your network traffic based on departments or some sort of internal setup within the company. You're borrowing, again, based on the number of subnets that you need, as long as each department has enough hosts. Okay? So, essentially what you do is you start with the largest subnet with the most people in it, and you make your requirements based on that. Because you don't want to start with somewhere in the middle or somewhere smaller and then run out of addresses. Not have enough to take care of everybody. So, in this example, you can see we've got different departments and they all require a certain number of hosts. So, which one of these departments has the highest number of users in it? Sales. Sales has 40 hosts in it. So when I'm subnetting this network, I'm going to look at sales and say I need to subnet in such a way where I can have at least 40 hosts on a network. And when you look at the bit values and everything, your options are either 32 or 64. So really when I subnet, I'm going to have chunks of 64. And I'm going to have more than I need. More is okay, less is not okay. So when I subnet to get 64 bits, or actually 62 usable hosts, I'm borrowing 6 bits. So again, that's just the math and the powers of 2 that I'm getting that information. So when I look at this, you're going to see 1.0, 0.64, 0.0, this has been subnetted to with a /22. Okay. Now, the subnetting that we've been talking about divides everything into even chunks. Okay? That can, in some cases, waste addresses. Just like we just talked about, we have 62 hosts, we only need 40. Okay? So that does waste some addresses. So, looking at this, we have a /24 to begin with. We subnet to a /27. That gives us 32 chunks of 32. And you can see we don't always need 32 hosts, right? In this case, we only need 15, 25. So the way that we fix this is what's called variable length subnet masking, which just means instead of dividing things into equal chunks, sometimes the chunks are smaller or larger depending on the number of host addresses. So in this instance, we've not used several different subnets of addresses, so we want to try to fix that. Instead of dividing things into chunks of 30 usable hosts, we're going to have some chunks of those, and then some of these we're going to subdivide up into 4 hosts each. Remember we said point to point? When you see that lightning looking thing, the red lightning thing, the WAN connection, generally you need an address on one side and an address on the other. So you need maybe just a couple addresses. So here's what VLSM looks like. So we take the network portion, we get our dotted decimal notation, we have our prefix, the /27. So 0 through 6 are subnetted as we did before, right? 0 all the way to 6 are subnetted as we did before. But because there are 5 host bits in the subnetted address space, we can borrow 3 more bits, right? Because we have 8 total bits in the last octet. We've already played with 5 of those, but we've got a few more bits to work with. And that can leave 2 bits in the host portion. The calculations are exactly the same, but instead of having one chunk of 16 addresses, you can break it up into 4s. So you can tell that that's happened when you see this prefix change. And you're gonna have a couple problems on this, but this is how this is working.
The basics of VLSM, or variable length subnet masks, works like this. 1. Subnets do not have to be equal sizes, as long as their address ranges do not overlap. So we can create unequal sized subnets. They do not all have to be the same size. 2. When creating subnets, it is easier to work from larger to smaller subnets. So for example, I have the 192.168.1.0/24 network. I subnet the network into 4 subnets /26 subnet masks. So the subnets go up by 64. I now have 4 equal-sized subnets. With VLSM, or variable length subnet masks, I can decide that I want to change one of these subnets and further subdivide them into smaller subnets, as long as the address spaces that I create, the subnets that I create, do not intrude into the other subnets. For instance, I could take this 192.168.1.192 subnet. The address range for this subnet goes from 192 all the way up to 255. What I can do is I can say, instead of having this subnet /26, what if I take that address space and divide it into 2 smaller subnets, size /27 each? If I do this, I effectively have created 5 subnets. The 3 subnets up here are 64 hosts each, and the 2 new subnets that I created from the 4th subnet are 32 hosts each. The reason I can do this is because my 2 smaller subnets do not intrude into the larger subnets. This is variable length subnet masks. In this situation, it has also allowed me to create 5 subnets, thus escaping the equal-sized subnet limitation of creating subnets in powers of 2. This gives me greater flexibility and allows me to create subnets of different sizes based on the requirements of my network.
Okay, so that is VLSM. Here we have it again in practice. We have smaller subnetworks that are going to connect these routers because they're just point-to-point connections. And you can see in router 1 for the configuration, it's been given the IP address 20.1. You can see the subnet mask has changed between building A and building B. You can see the different serial connections. So this is the connection into the LAN, and this is the connection to the different routers. So you can see the subnet mask has changed to allow us to just have little bitty subnets to connect those 2 routers, because they really only need 2 usable addresses. So we can tell that VLSM has happened because that CIDR changes. We had this 224, we went to 252. That means that our prefix changed. Here we have again in practice from router 2, gigabit Ethernet 00. Then we have our serial connection this way, our serial connection that way. They've been assigned addresses within their given range. For router 3, the same thing. Off to our network, then serial 00 and serial 01. Then we get to router 4. They have connectivity here to their network, and serial 000. What happened to 001? It's not connected to any other router, so we don't need it. Right? But they've interconnected all these using VLSM. This is an example of what the IT department might keep to keep track of all these addresses. So we have a bunch of statically assigned addresses, which means that we have to keep track of what's used and what's not used. So an addressing chart can identify the blocks that are unused, what are used, and what the hosts are in between. So this is for our /27, and this is for our /30, and you can see that these are allotted to those WAN connections, and they've only got 2 usable hosts in each one, because that's all that's needed. So you can design this. It still leaves these 3 unused, but then if we add more buildings later on, we can allot those addresses to it, as long as we're keeping track of it properly.